Good morning, everyone. I want to thank Jonathan and his team at ARMS for inviting me to speak to you today. And my intention today is to provide a little bit of food for thought that comes out of some research we've been doing over the last couple of years into the Internet of Things. My background is in HPC, and then I did cloud computing for a while, and most recently we've been doing Internet of Things. And we think we've discovered some things that are somewhat startling, which I want to share with you today, and hopefully will stimulate some interesting conversations as we go forward. So let's talk about the Internet of Things. You've seen these slides. That says 50 billion by 2020. That you can't see, but it says 75 billion by 2025. The numbers keep getting bigger. That's 1 trillion. Okay, it's large. And this is this idea that there are going to be lots and lots of devices hooked up to a fully interconnected network, and they're going to be talking to each other. And when we start talking about 1 trillion things that are powered and programmable and communicative, it is really a different realm from what we're used to. Okay, and so we've been doing this for a couple of years. We decided after lots of experiences with commercial cloud computing to go out and look at what could we do today if we started putting lots of things on the internet. And I want to make 3 observations that come out of those experiences. The first observation is that we're all worrying about the wrong thing. Power is what you have to worry about. If you're going to put things on the internet, you're going to put 1 trillion things on the internet, you got to worry about power. Think about if every one of those things is 1 watt, and it's on all the time, 24/7, trying to tell you something. That's 1 terawatt, right? It's not going to be 1 watt. So you really have to worry about power. Second thing is, it's more than software. This is something cloud computing understands. When you write a cloud service today, you write a deployment program. But when you write programs for, say, HPC or whatever, you typically don't. And in this space, you must. And I will try to explain why. And the third thing is, you build for repurpose and not purpose. Most internet things today are purpose-built. It's a sensor. It's manufactured. This is not going to be the future. And this really speaks to what I'm doing here today, which is ARM makes really, really good power-efficient, deployable, repurposable processors, which I think is what the future needs. Okay, so let's start. That's a data center. It's probably Google's data center. No one's really sure. It's on the Columbia River Gorge. 5 miles to your right is a hydroelectric plant. 92 megawatts of that hydroelectric plant is spoken for by this data center. So it's a large, purpose-built device, and it's very, very power hungry. And the model for Internet of Things is that data center has got to pull data from there. That's a citrus orchard about 1,000 miles away in the Central Valley of California. It's routinely 45 degrees Celsius in the summer in this location. If you're not seeing our IoT deployment, don't worry. There it is. The problem we're doing here is frost prevention. If you grow citrus in the Central Valley, during the winter time, particularly near the Sierras, it gets very, very cold on the ground. 30 feet up, it's maybe 3 or 4 degrees warmer. What you want to do is mix that air. And those little propellers that you see, that's actually a 30-foot tower. This is from 1 kilometer, right? Well, and the small circle that you see down by the water, that's a thermometer. So your goal is to turn on the fan when you've got a 4-degree Fahrenheit temperature inversion and measure the warmth at 1 meter. Because if you don't, you lose your entire crop. And this is a farmer's livelihood. If they lose that crop, if they lose that growing block, they make nothing that year. So the stakes are pretty high. The way this is done today is you pay an army of people time and a half to stay up all night and drive around in a truck. And they drive out to the fan, and they take a measurement at 30 feet, and they take a measurement at 3 feet, and then they turn the fan on, and you gotta be very careful. That thing is powered by a propane motor, a V8 propane motor. You gotta stand back. It's very dangerous. This is an industrial work site. Doesn't look like one, but it is. What we decided to do was try to not have people out there all night measuring the temperature, but try to automate this process. And so I'm gonna tell you a little bit about what we've learned. First thing is power is the problem. To put 4 PC-class machines out there to do image detection, motion detection, temperature readings, humidity readings, all the things you need to do frost prevention, costs about $20,000 for 4 PCs. Not only that, it's a 10-foot pole that goes 4 feet into the ground. You've got lead-acid batteries in the middle of a growing region, and they're trees. You can't stand things up that look like trees when you're growing trees because tractors hit them, right? So you have this huge industrial problem out in the middle of nowhere. The reason that picture is so small is that's the nearest place I have power. Let's see, I'll show you again. That reservoir has one 110-volt plug, which is in a pump station. And the nearest we can get to those fans is 1 kilometer. The nearest internet is a kilometer behind you. So you're really talking about a 2-kilometer space. You've got no power, you've got no network. Okay? Power infrastructure is fragile. If you do this with solar, you've got batteries, they fail, particularly when they discharge. If they're lead acid, there's the sun angle you have to worry about, and it changes over the year. Dust and bugs and other things that come from animals can be a real problem, so you have to worry about losing some of that power. It's invasive. You stand things up. You can't trench. I can't run a conduit a kilometer from underneath the reservoir or around the reservoir, so you have this problem. You can do long-distance Wi-Fi, very, very power inefficient. Right? And the scaling properties are really, really bad. The more power you need, the more expensive, fragile, and invasive your system becomes. So the first thing you have to worry about in this space when you're doing IoT is not the I or the T, it's power. Okay, here's the second point. What's wrong with that picture? Yeah, clearly, that's an environmental sensor, that thing that looks like the lunar module there, and it's measuring CO2. It's a very, very sophisticated device. It's about $250,000. The little cage you see in the left front, there's actually a pump. It's pumping water through the ground to measure sequestration in the soil. Not only that, it's measuring CO2 content in the atmosphere. The problem, and there you can see the solar panel, lead-acid batteries behind it. The problem is it's actually in the wrong place. This thing was designed to sit at least 50 feet up in very rocky soil in order to get a sequestration measurement. The measurements are useless from that device, useless. It's in the wrong place. It's in the lowest spot that you could possibly put it in that growing space. Why? Why did that happen? And it was abandoned 18 months after it was installed. This is a big California-funded carbon sequestration project which just went defunct, right? And the question is, why? Why did that happen? The answer is because when they did the development, the deployment people weren't in the room. There were a bunch of people who built that system. There were a bunch of people who programmed it. There was a project manager. They did this all over California, and then they contracted the siting. And those people were not part of the agile development process. And the contractor comes out and says, look, this thing is big and it's heavy, and I've got these solar panels. Let me put it in this wonderful spot, which is exactly the wrong place. So when you're doing IoT, the second point I want to make is deployment is part of the development process. In cloud space, we know this. In HPC space, not so much. In IoT space, it is absolutely essential. Okay, what went right? Well, they gave it to us, right? $250,000 of equipment. Here, Rich, do you want it? And I said, yes, absolutely, I want it. Who wouldn't want this amazing sensor? But then I took on a whole bunch of problems. The first thing is that it's built for a very specific purpose. It's this Campbell Scientific data logger, super calibrated stuff that isn't producing any useful data. Now, I can reprogram it. It's very, very hard. I can't move it. Right? It costs 2 man days, 2-person days, to site that thing. And if I want to truck it up the hill, it's probably $50,000 if it's a penny. I don't have $50,000. So what I need to do is repurpose that thing in place. And this is the thing about IoT. You got 1 trillion devices, and one of them fails. You're not walking out there and replacing it. You're not replacing 1 trillion things. What you're going to do is reprogram them. You must have repurposable devices, because they're everywhere. It's going to be everywhere. And they're going to fail and break and be misdeployed all the time. So we can't be thinking about purpose-built centers that you rip and replace. We have to be thinking about repurposable IoT devices. And that's the problem with this. I want to repurpose it. I am reprogramming it. It's incredibly hard, and it shouldn't be. Okay, so in 2025, when N billion of these devices show up, there are 3 things that I predict will be true. Power will be the big issue. Deployment is a first-class programming activity, and these things must be repurposable. Okay? And so if you take that to be true, and I'm not saying you should, but we have after many, many failures, you come to a surprising conclusion, which I hope to try to substantiate in the next 34 minutes, and that is that the internet at present is built backwards. It's built backwards. What do I mean? Okay, this is the cloud today. Large e-commerce companies primarily, although tech companies are trying to get into this business, run fabulously managed, super power efficient, but not low power data centers. And the data flows from the data center to the eyeballs, right? If you think about an e-commerce shopping experience, or Netflix, or Facebook, the data that comes back from the people are clicks. What you click on encodes a preference. And if you're in the e-commerce business, that's what you want. I want to know what you want to buy. In economic terms, that's called a preference. And the way that we learn those preferences is by watching your clicks. That's a very small amount of data. So from your left to your right is almost no data moving. But from your right to your left is a lot of data. You're watching videos. You cannot watch a news story today that's a paragraph. You got to watch a video. It's a tremendous amount of data flowing the other way. And that engineering, that asymmetric engineering, is significant. CDNs, Level 3, Akamai, all these companies are built to move data from your right to your left, right? And so cloud today is read-dominated, and you're really trying to run big data, right, over big data, which is lots and lots of people, and you're running big stats. And the reason this works, it's important to understand that that model makes a lot of sense, is because you have huge sample sizes. If I'm trying to make an inference about what you will buy, I'm using statistics in a backwards way. Statistics is inference about a population. Now we're making statistics that are inference about you, not a population, about an individual. That's backwards. That's not what statistics was invented for. And so if we're going to make individual inferences, we need huge sample sizes so we can make population samples of people who look almost like you and make an inference. That's why it's a big data problem. Okay? That's IoT. IoT is trillions of devices sending lots of data to the cloud. And almost nothing goes back. It's backwards. Furthermore, the data that you're sending is little. There's lots of little data sets. So it's not big data, it's big little data, right? Every one of those sensors wants to send you a whole lot of information. But if I open my refrigerator in California, does someone in Boston really need to know? I have this conjecture. I don't claim this is true, but here's my conjecture. The actionable relevance for a sensor and the data that it gathers decays like the square of the distance from where you gather it. For sure, when I open my refrigerator in my kitchen, things in my kitchen might want to know. But things in Boston don't. Right? Now, yeah, if I want to sell you a refrigerator, I need that data. That's an e-commerce problem. But if I'm going to take an action based on IoT from these trillion devices, if it's not just a big e-commerce exercise, we're shipping the data the wrong way. Okay? I also have this theory, and this is sort of the motto that we use when we engineer things in my lab. Move the data as little as possible. Compute is super robust. I can recompute dense linear algebra all day long, and it gives me the same answer each time, and it's really, really fast, and it's really efficient. But as soon as I start moving the data around, bad things happen. I get it in the wrong place, the schema's wrong, we lose a disk, there's some network problem that prevents it, not all of it makes it. Moving the data is where the failures occur. So you move the data as little as possible, right? And when you move the data, particularly if you're using radio, where the amount of energy you need goes like the square of the distance, it's very power inefficient. So you want to keep the data near where you gather it for relevance reasons, and moving it is a bad idea, right? However, that's your future if you buy what the public clouds say. Right? This is from a colleague of mine who teaches an IoT class in Germany, but also came and spent a year at Santa Barbara. And essentially, that's Amazon's IoT architecture. And the little dotted line is the cloud, and the thing on the left is the device. And the idea is get the data out of the device into the cloud as quickly as possible. That means I'm going to set up a bunch of devices in Visalia and send the data 1,000 miles to a data center in Northern California so that as raw data, it can be processed, right? That's the new model. And it's kind of a silly model in the sense that often when you send telemetry, low-level sensor data, you're combining it in an aggregate, so you send it and you throw it away. You average it into something, or you take the max, or you take the median, and then you throw away the raw data. So we're spending all that energy and removing data all that distance, which is dangerous, and we don't need to. Okay? So the internet is built backwards. And the reason for it, the reason that we have built it backwards, the reason is because we've adopted a service architecture. Why? Why are clouds built from web services? Well, first thing about a web service is it reacts to user activity, and that's a good thing if you're in the e-commerce business. You want the cloud to do something when someone clicks. You don't want it to be doing something all the time. You want to wait for the user to do something and have it be active. And it's very efficient. It's power efficient, it's speed efficient, it's dollar efficient. That's a great way to design a reactive system. The second thing is services are abstractions, and all of the gory details like deployment programming and reprogrammable issues and engineering are hidden behind a service interface that looks like a web browser. That's super useful as far as being repurposable. Clouds are super repurposable. Netflix doesn't look the same on any 2 days. That's not an accident. Right? And the third thing is, of course, these are reprogrammable, right? You are basically in the business of constantly upgrading not only the infrastructure that you're using because it's more power, cost, or speed efficient, but because you need to improve the services that are being deployed. So clouds are built from services. If clouds are built from services and the smarts are in the service, what you need to do is move the services to the devices. We need to invert the model. We want to run services at the edge and applications in the cloud. Makes sense. The data's at the edge, the smart's at the edge. You're trying to take an action at the edge. You want the things that users do. You want user interfaces and user applications in the cloud, and you want power efficient, programmable deployment, and repurposable services at the edge. And so we need to flip the internet. And this is what we call devices as services. The key thing is it's multi-scale. You have to have a way to program a device, a small edge device, a cloud service, say, running in a private cloud, and a public cloud in exactly the same way. Otherwise, you've got 4 programming problems, and actually in each one of those things, you've got 7, right? You had to do 7 different interfaces to get an IoT device to work in AWS. If every one of those things is 7, nobody's programming this. It's way too heterogeneous. So we said, okay, we want to be able to write multi-scale programs where scale talks about the size of the device. And you can think of it as how much power does the device use. That's a good proxy for scale. Okay? But it also gives you deployment support. You have to be able to move the code around, right? That's deployment support. If it's the same code that goes everywhere, then you can solve the deployment problem, and it has to be reprogrammable. And so we started looking at this, and it turns out that the cloud people have been working on something for a few years called functions as a service. If you haven't seen this, it's really a functional programming model coupled with event-based programming. So you write stateless grains, what we'd call them in HPC, and you write in a high-level language like Python or Java. And then there's a service, and that service takes that grain and all of its dependencies and packages it up and hooks it up to a web server. And when a request comes in, or someone stores something in a database, or some other event happens, your function is triggered. And it's passed a set of arguments, it executes, it can save no state itself, it has to call some other service to persist. So the grain itself is functional. It's super efficient. These things are run in containers so that they get isolation, but that's not the point. The point is it's just a straight line piece of code, not threaded. Super efficient, which makes it super cheap. You can build auto-scaling websites out of functions as a service really, really cost effectively. Much more cost effectively than if you rent the infrastructure and run your own web servers. Okay? It's also really complicated. You have millions of these functions firing. There's an event-based model, so you're writing a function and an event filter. Event-based programming is notoriously hard in the real-time space, and that's kind of what they're asking you to do, but you can save a lot of money by doing this. So we said, okay, let's take that model, that functions as a service model, and let's extend it to make it work in this space. And that comes up, so we came up with this thing called the Serviceless Platform of Things, SPOT, and the idea is to take FAS, functions as a service, and add append-only storage, so you get data integrity, and code portability. right? And along with that, some debugging support and fast runtime things. If you're not sort of interested in the gory details, think of it this way. Spot is a functions as a service platform, which is portable to multi-scales that allows you to write the same service to run everywhere, from a device controller that's got 32K of memory up to a public cloud. Same code, same model, you can just move things around, okay? It's open source, if you're interested in this kind of thing, please join us. I have time for one quick anecdote. It used to be called CSpot, and the reason is because I wrote this in C. This was the thought experiment. What if you wanted to write FAS that ran anywhere? I said, well, of course, if we're going to write on a microcontroller, run on a microcontroller, we got to write in C. So I wrote in C. And we have this research meeting, and I show up at the research meeting with my graduate students, and if you haven't seen this lately, when you speak to graduate students, you're speaking to people who are doing this, right? You know, and they're doing this, and I'm saying, okay, I'm here and I'm fixing the internet. And they're like, oh, he's fixing the internet. Wow, Google pigs fly, that's awesome. And then I'm going on and on about this and how the network is backwards and all this stuff. And they're like, yeah, network is backwards, oh, cat videos. And then pretty soon I say, and you're gonna help me. And they say, what? I said, yep, we're writing papers about this. For the next year, we're writing papers about us fixing the internet, and we're writing in C. It's so freeing, it's wonderful. You can run on anything. You can run in Amazon. Look, it's fantastic. And they're like, C? I'm like, yeah, you're gonna program in C. And they went, okay, can we have access to the GitHub repository? And I said, sure. Within an hour, they'd written a Python binding. So next time you think, wow, academia is really an old folks' home, you're not incorrect. It's just an old folks' home that is almost exclusively populated by young people. They're very stubborn. Man, I thought I was Dr. Timothy Leary at the John Burster Society for Python, right? Look, C, it's awesome, it's mind expanding. Yeah, Python, we gotta do Python. Okay, so that's my anecdote. Bottom line is, it's called Spot and not CSpot because it's multi-language. And it had to be, because that's the only way I could get the graduate students to work on it, but they do. Please help us. If you'd like to do another language binding, or if you like C, please, we could use your help. Okay, this is not a fake system. This is actually existing. This is our Smart Farm project. Smart Farm is the attempt to do frost prevention. We're also doing differential irrigation for almonds. We're looking at Asian citrus greening disease. There's this psyllid that just wiped out the citrus industry in Florida. California's terrified of this. So there's a bunch of remediation things that are going on. We're building the instrumentation out of Spot, formerly CSpot, for it. And the way it works is this, is that we run Spot on everything. We run it on drones, we run it on Raspberry Pis, it runs really well on the ARM, we run it on microcontrollers, and we put it out there, a kilometer away from the nearest power. Where there's power, we run an edge cloud. We take a bunch of fully purposed processors that are hardened, because they gotta live in a very, very hot and hostile place. We run a small cloud infrastructure on it. And that lives in the remote location where there's power. That communicates over usually common carrier internet to UCSB, where we run a larger cloud that is purpose-built for research. So we're not doing pay-as-you-go kinds of things. And then if we need to run image recognition or SageMaker or these other kind of high-level services, we can use the public cloud tier. So that's what it looks like. We think that's what the future looks like. And the key thing is the data moves from left to right only as far as it needs to. If we're gonna do image processing and we can do it on farm, we do it on farm. If not, we do it at UCSB. If not, we do it in the public cloud. This is both cost efficient and speed efficient, which means it's power efficient. Okay, here's my one data slide. We sat down to do this, and we built it, and then we benchmarked it against AWS Lambda. AWS Lambda is the leading FAS offering. It is AWS only. So when you run an AWS Lambda, you run an AWS. It's not a distributed architecture. It doesn't run on run on even multiple regions within AWS. Spot is 2 orders of magnitude, 1 or 2 orders of magnitude faster than AWS Lambda. Now, that should tell you something. This is a bunch of graduate students and me, and we are not 10% faster. 2 orders of magnitude faster. And there's an army of people at AWS working on Lambda. Why? And they work on the performance of this. It's all about that. And the answer is because we're not stuck with a legacy. We're taking a clean slate approach, right? We're not sitting there saying, oh, we have this big infrastructure and we have to leverage it, and how are we gonna get it out to? We're saying, what if you wanted to do IoT? I'm not saying that what they're doing is wrong. I'm saying that legacy has a 2 order of magnitude performance penalty, which is a power penalty, at least, right? Because we're not that good. So this tells you there's a lot of room here. There's a lot of room to improve on what everybody tells you is unimprovable. The Googles and the Microsofts and the Amazons of the world have got cloud sewn up. No, they don't. Because that's a research experiment, right? If we got a bunch of engineers, how much better would it be? Okay, so I'll start to wrap up and then take a few of your questions. What's the brave new world going to need? In my view, it needs one ring to rule them all. Right now, we're doing source code portability. This is the wrong way to do portability. It's the right way to write a research paper, but it's the wrong way to do portability. And we would love, in fact, try and ship binaries whenever we can. There should be a universal processor architecture, and it's not a microcontroller. It's got to be repurposable. If you haven't tried to program a microcontroller, don't. Often, you're stuck with a memory stick and a Jeep, right? You're going to drive out to this thing, and you're going to plug a memory stick in and hope that it reprograms. Some of these things aren't even reprogrammable over the radio. Even if you had a radio connection, which you do not, right? Not a reliable one, you can't do it. And if it's one of these Zigbee LoRa things where you get 25 bits a second or something like that, you're not reprogramming it over the radio. This is not the right answer. We need low power, general purpose, multi-scale architectures. We need ARM. Okay, there are a whole bunch of problems that we haven't even thought about, right? So now we got all these sensors, and they're out there, and they're running on everything, and they're running Spot. Lovely. How do I find them? Sticking them on a web page, not great. You want some sort of distributed infrastructure. Oh, the blockchain people like us. Wow, yeah, we could do this thing where you publish this ledger about where the sensors are and who owns them and their security policies and smart. Yes, you can. How power efficient is it? This is where we part company. Because that blockchain stuff's not super power efficient. You want to do some research? Figure out how to do a distributed, unforgeable registry that's power efficient. Huge problem for IoT. Okay, this that I'm telling you about now is assembly language. These programs are incredibly hard to write. They're incredibly difficult to debug. We built in a bunch of debugging functions, and they're helpful, but really, you want to be able to program the IoT in high-level languages. You just want this ultra-efficient runtime, right? So think of this as being a really, really efficient runtime that needs the programming language support on top of it. Is there an operating system? Yeah, C Spot runs native on some devices, and it runs as a guest on others. It's kind of universal operating system support, storage, communication, computation. But there are no types. There's no language semantics. There's no notion of Turing completeness or Lambda functions or whatever, Lambda calculus involved. So for sure, there's a whole stack of things that needs to go on top of this for this to be real in any meaningful way. But we started with assembly language when we did CPUs. We're starting with assembly language now. Okay, so now I'll make some predictions. What fun would this be if we couldn't make predictions? First thing I'll say is HPC is really going to matter. This drives my cloud colleagues nuts. Right? So I was an entrepreneur at one time, and I have a bunch of friends who work in the cloud space, and they call me all the time, and I say, you really need to think about HPC, and they're like, Rich, stop it. You're a college professor. Take off the propeller beanie. And I'm like, no, seriously. The reason is because a lot of IoT is making inferences about the real world. E-commerce is not. E-commerce is making inference about what you want to buy. That's an intellectual that's in your head. So we don't need a simulation of the real world to know what's going on in your head. It won't do us any good. What you do for IoT is simulate the real world. I give you a bunch of telemetry. Here's the temperature. Here's the wind. Here's the wind direction. Here's the humidity. Where's it going to frost? I need computational fluid dynamics. So the back end for this stuff, yeah, there's going to be Hadoop trying to figure out, will you buy a new refrigerator? But the IoT piece of it is going to depend on HPC. So it's the right combination of HPC and cloud that's going to make this go. And I think people miss that pretty consistently. As I've mentioned, it's a tiered cloud architecture. And it may even be a tree, right? We can't tell if that registration layer is a blockchain, it's a big flood network or a ring. I've got a student who's building a DHT for it. We'll see. But the bottom line is you're going to have tiers. And these tiers offer various classes of service, and they have various power and speed requirements. And moving the data is going to be how you're going to decide where you're going to go from tiers. But the thing is, you're going to start at the outer tier and work your way in, and not vice versa. Don't believe what Google and Amazon and Microsoft are telling you. It isn't going to be happening in the cloud. It's going to be happening at the edge. We're very interested in studying this problem end to end. Obviously, this is very application-driven research. We go out and work with farmers. I've got sunburns. I've got cuts and bruises. I have a hat and boots when I do computer science in the field. And the part of it that UCSB is excited about is the idea that we can study energy efficiency in this new space end to end, from the electrons to the data center, throughout those tiers. And Brent Gorda, who I've worked with in the past on various projects, is very interested in understanding how ARM can help optimize that process. And there's a new institute, a couple years old, at UCSB, where we're building an experimental data center, where we have a data center that's thermally instrumented and power instrumented. So we can do very fine-grained end-to-end studies of where the efficiencies are in this very complicated new world. And we're hoping to partner with ARM to do that. I will say this. This is my prediction as a former entrepreneur. The company that figures this out is the company of the next decade. It is the Microsoft, the Google, the Intel. This is coming. You can see the future. There is no question this is coming. I can't tell you what to do about it today. I can't tell you how you make money on it today, but you know what's going to happen. This is going to happen. And I think the company that figures this out first wins. And my sincere hope is it's ARM. ARM actually has the leadership position in this space right now. Right now. So hopefully, at least for the purposes of this talk and maybe the rest of the afternoon, we can have fruitful conversations about how realistic that prediction is likely to be. But that's what I believe. Next thing I'll say is this is going to shake up the way you hire talent. I don't know if you've seen this before. We have lots of graduate students, and these graduate students want to work for the cloud companies. The cloud companies pay them infinite amounts of money to come and work for them. It's amazing. It's great. They're really smart. These graduate students are so good. Oh my God, so they're worth it. They're completely worth it. But to get a job at this cloud company, the cloud company says, okay, please code binary search tree in Java. Okay, that's how you get a job at one of these companies today. That's over. What's going to happen is they're going to say, show me your deployment. Show me your crash logs. Where is your code running? Not what have you written. Not can you code binary search. The cubicle days are coming to an end. And you're going to want people who actually know how to put things in that shed. That tin shed there on the right, that gets to be 130 degrees Fahrenheit in the summer. 130 degrees. You've got to make a system run 24/7 to irrigate the almonds in that environment. Almost anybody can write a piece of Python code to run in their lab. Very few people can do that. They're going to rule the world, and this is how you're going to want to interview them. And then I'll wrap up and take some of your questions. This is a team effort. Computer science is now a contact sport, no question. The future of it will even be more of a contact sport. It's multidisciplinary. You have to be crazy to let me and my graduate students come out and instrument your property, right? I mean, and there are lots of crazy people who will do it because it's such an important problem, particularly in California where things like water and climate change are having an immediate economic impact on a lot of the people we work with. You can see some of them. There's some startup companies. There are folks who run professional orchards, ecologists. There's these ecological centers that we work with. There are a lot of companies who have been very, very generous with their support for this. Pay attention to those pictures. That's the future of technology on the right. Those people are unbelievable. This is all joint work between me and Dr. Chandra Krintz, who is really the person who has been forwarding the smart farm effort, the analytics, and the stuff that sort of sits on top of the systems. It's a really, really good partnership. He's also super connected with all of our collaborators. If you have any interest at all, please email us or seek me out at this meeting. I'll just stop there and spend a few moments taking your questions. Thank you so very much for your attention.
So you may chalk it up as legacy, which is fine. But a lot of the engineering that went into the stuff like AWS Lambda was around security and isolation. And you didn't talk very much about security and isolation.
Yeah, no, good point.
So
very, very good point.
Be interested to hear what your
yeah,
approach
so for sure, there's a huge security and isolation problem that you've got to solve in this space. We are solving part of the security problem today using hyper-fast capabilities, right? So you have to make a decision about how you're going to secure the system. And so far, we have a plan and a small implementation, although it's not fully fleshed out, for how to do authentication. So we don't have discovery yet, that's that blockchain piece. But if you know where something is, we can make sure you're authorized to see it in a super power efficient way. A way that runs on microcontrollers, won't drain your battery, works on a duty cycle. That took some thinking. It's not easy, you're absolutely right. But it's just authentication, there's no privacy. The privacy question is a real thorny question. And it's at the last mile. You can make things private from the time you hit the power. Because to make things private, you can run encryption, and encryption is incredibly power hungry. So the model is, as soon as you find power, wired power, encrypt. And that gets you part of the way, but you have this piece where you've got a low power radio, and the question is how do you secure the low power radio? And we don't have a good answer for that yet. So there's a privacy piece, and that part's open. If you walk up and you war drive our Zigbee, for those of you who are tech heads, you can do it and get the data. And we're working on that, and we're working with other researchers and companies to try to figure out how to solve that problem. The data sort of security problem is actually no worse than it is in the cloud, in the sense that once you've got the data, the same sort of security mechanisms that you use to protect it work. They just have to work at the edge. But we've been really good at building open source replicas of the public clouds that run at the edge. Satoshi knows, Satoshi's sitting next to you. Hi, Satoshi. Satoshi and I are old colleagues, and we built for him a few of these things way back when. So we can move a lot of that security mechanism to the edge. We just can't get it on the device yet. And then there are new problems, like, okay, let's do the registry with blockchain. Now everybody can see where the sensors are. Is that really what you want? This is what some people want, and there's some good reasons for that, like if they're government environmental sensors or something like that, but it may not be exactly what you want if you're a farmer. So, huge problem. Good news here is all of that does use containers for isolation until you're on the microcontroller, and then it's a microcontroller, which is its own isolation container. So really, that part of it, we're just lifting from the cloud space. It's a great question, though. Yes, sir.
Ben Lee from Duke University. Thanks for the talk. Question about, and I totally agree with you about data movement and the performance and energy overheads, but part of me wonders whether data movement to the cloud is unavoidable for data aggregation and machine learning on it, right? So,
yeah.
So to what extent do your end devices on the farm, and they're doing frost prediction, do they need information from adjacent farms or farms in the Midwest?
Yeah, it's great.
Right?
There's this question of aggregation that comes up all the time, and your inclination is to put everything in the cloud so that you can have it all in one place and mine over it. You're absolutely right. Let me tell you the following story. We were in North Dakota and giving a talk, and this is in the middle of the drought in California last year. And we said, we're working on the water problem for farms. And we were trying to figure out groundwater and subsidence using IoT. So I said that, and one of the people from the ag industry in North Dakota says, thank God someone's going to get rid of all the water. I'm like, what? They said, oh yeah, it's a real problem. When it melts, there's water everywhere. We get root rot, and the tractors get stuck, and we got to get rid of the water. It's a drainage problem. I'm like, no, it's not. I want the water. Okay, turns out the answer to that question is regional. What I do in California makes no sense in North Dakota. So yeah, you can put it all in one place, but you're putting it all in one place, and you're not really thinking about the locality. IoT is going to be about locality. Now, with that said, there is some locality for every aggregation event that makes sense, okay? The locality that makes sense in your case is really at the county level. At least in California, we regulate farms by county. So what you want to do for a lot of applications is put the county data in some place, but it's not a public cloud. It could be a regional cloud, right? And this actually helps you with security because you can physically secure that, and then, if you're good at it, right? And it's localized. So you're cauterizing the damage that can be done if you leak information. So the key thing for that is you move the data up the hierarchy to the point where you have sufficient locality to solve your problem and no farther. Okay, I've worn you out. Thank you so very much for your attention today. I'm going to be around all day. If you'd love to tell me how wrong this talk is, I would love to hear it. Thanks again.
Awesome. Thanks. Hold on. Wait.